Okay, in this video we will be going over resonance in RLC circuits. And to begin, we will be talking about how each of those individual components, a resistor, inductor, and capacitor, all work in an AC circuit. So an inductor, when we have an inductor in series with an AC voltage source, as shown in figure A, a sinusoidal voltage is applied to the inductor, and we can see that by this green line in the graph. However, the voltage leads the current by 1/4 of a cycle. This is because inductors oppose change to current, acting as an effective resistor to the alternating current. Inductive reactance measures the opposition of current flow and is measured in ohms, just like resistance. So the inductive reactance and induction, as you can guess, are proportional to one another, meaning that as induction increases, so does the resistance to change. Inductive reactance also increases as the frequency increases, and we can see that by this equation on the right-hand side of the slide. And this is because the greater the frequency means the greater the change in current, which creates greater opposition from the inductor. Okay, now a capacitor connected to an AC voltage source. So as voltage across the capacitor and current are graphed as functions of time, we can see that the current begins at 0 when the capacitor is fully charged, and as the cycle goes on, the voltage lags behind the current by 1/4 of a cycle. So this is the opposite of what happened with the inductor. The capacitor is able to change the current, stopping it completely when it is fully charged, and so the larger the capacitor, the greater the charge it can store, and the greater the current that can flow. The greater the frequency, the less time there is to fully charge the capacitor, so it impedes current less. So basically, the capacitive reactance is inversely proportional to both the capacitor and the frequency. And now resistor is connected to AC voltage source. The current and voltage are exactly in phase with one another. Neither one lags or leads the other. So now when we combine the resistor, inductor, and capacitor in series to that AC voltage source, we can't just combine all of the total resistances, even though each one of those components impedes current when they are alone. So when they are combined, we can measure the impedance. And that is shown by this equation at the bottom. Inductors and capacitors act in opposite ways, and so that allows them to at least partially, if not totally, cancel out each other's effects. And we can see that by these two graphs over here. If we were to superimpose them, we could see that they would at least partially cancel each other out, if not totally, just depending on the magnitudes of both of those. So getting to resonance. So as mentioned before, the reactances, both of them vary with frequency. The inductive reactance is larger at higher frequencies, and the capacitive reactance is larger at lower frequencies. But if we have some intermediate frequency going on, the reactances will be equal and they will cancel out. And this frequency is called the resonant frequency. And when this happens, impedance is equal to resistance, and the current is at its maximum. And we can see how we can solve for that current using this equation. So when we reach that resonant frequency, these two reactances are going to be equal to one another, and they will cancel out, and this will result in a larger current. This equation right here is the same thing as this. We're just replacing in the actual formulas for inductive and capacitive reactances and setting them equal to each other. And then if we solve for F naught, or the resonant frequency, this is the equation we get, and that is how we can solve for that resonant frequency. And this is very important in the real world, obviously, as all physics is. It is especially important with radios. So there you go.